Now? Okay. Hello, everyone. Thanks for joining us for October's Deeper Talks, the SURF Seminar Series. Before I introduce today's speaker, let me just go through a few logistics items. There will be a Q&A period at the end of the presentation. For our online audience, please put those questions in the Q&A section on Vimeo. And for those attending in person, raise your hand and we'll get a microphone to you. You can ask the questions here in person. This talk will be recorded like all of the Deeper Talks series and will be available on the Institute website. And without further ado, let me go ahead and introduce our speaker today. Dr. David Woodward is a physicist at Lawrence Berkeley National Laboratory who's been working on direct search for dark matter now for over 10 years. He obtained his PhD from the University of Sheffield in 2017, then worked at Penn State University as a postdoc and research assistant professor before moving to Lawrence Berkeley Lab in 2023. This journey included several years working at SURF during the construction, the commissioning, and early operation of the LZ dark matter experiment. Woodward co-led the publication of LZ's first results and served as the experiment's run manager between 2021 and 2023. He's currently LZ Assistant Operations Manager and serves on the SURF User Association Executive Committee. David's no stranger to SURF, and we're happy to welcome him today to talk about mining for WIMPs with the LUX Zeplin dark matter experiment. Thanks, Dave.
All right, so yeah, thank you for the introduction, Jarrett. I just wanted to say it's a real pleasure to be giving this talk to the SURF Institute. As Jarrett mentioned, I spent a lot of time at SURF building and running this experiment. And it really wouldn't be where it is today without the help and support of everyone at SURF, not just those that worked on the experiment directly, but everyone involved in the operation at SURF. So very happy to be giving this talk. So let me just begin by introducing the LZ collaboration. So we're 38 institutions, 250 scientists, engineers, and technical staff spread across 4 continents now. And this is a picture of our collaboration at a meeting we had at SURF last year. What are we doing? Well, this is the biggest picture summary of our current understanding of the universe. So we know that the universe is made up of 3 components, dark energy, which is this thing that's somehow wrapped up in space-time and is causing the expansion of the universe. And then matter, which moves around, and there are 2 types of matter. We have the visible matter, the stuff that we can see, and the dark matter. And this picture on the right-hand side is actually some data from the Planck spacecraft studying the cosmic microwave background, which is essentially this radiation that's left over from the Big Bang. And by studying the anisotropies of this picture, so the differences between the dark bits and the light bits, you get some understanding of the substructure of the universe. And so what we can do is take this model where we have our 3 components and ask how much of those components do we need to look like this picture on the right-hand side. And it turns out that we need 26% of the universe to be dark matter. And there's about 5 times as much dark matter as there is ordinary stuff. So the question we're asking is, what is the dark matter? What is it made of? What are its properties? Can we actually try and detect it? So there are lots of theories and models for what dark matter could be. I'm going to jump to the one that we're investigating with LZ, and that is weakly interacting massive particles, or WIMPs. So the motivation for WIMPs goes a little bit like this. So in the early universe, just after the Big Bang, everything had a lot of energy, everything was very hot, and ordinary matter was colliding and producing dark matter particles. Okay, so this process here on the left. At the same time, the dark matter particles were finding each other and annihilating and producing ordinary matter. So there was this equilibrium that we had in the early universe. But as the universe aged and cooled, there wasn't enough energy anymore to do this process of creating the dark matter. So that process turned off, and we just had dark matter particles colliding and annihilating. But then as the universe expanded, the dark matter particles got too far apart from each other, and this other process essentially turned itself off as well. And so we have what we have now, which is the abundance of dark matter in the universe, which we saw is about 26%. And it turns out to get this abundance, what we need is for the dark matter annihilation cross-section, so essentially the strength of this interaction with itself, to be at the scale of the weak force, the weak nuclear force, which is something we know about from a completely separate field of research, particle physics. And it's one of the fundamental forces of nature, the standard model of particle physics, which describes the particles and their forces, basically gives us this force. Okay, so this idea that there are these two independent fields of research pointing to the same thing, which is that there's the existence of a new particle at the weak scale that could explain the dark matter, is very compelling. And that's what WIMPs are, and that's what we're studying. So as an experimentalist, that's pretty much enough motivation to go out and try and build an experiment. How do we actually try and detect these WIMP particles? So to do that, you sort of need to understand that our universe is sort of like an experimental lab in of itself. So here's a picture of our galaxy, the Milky Way. We're on Earth, which is on one of these spiral arms of the Milky Way galaxy. And we're actually moving through the galaxy. So we're rotating around the center of the galaxy, and we're moving through this dark matter halo. So we're actually moving through the dark matter particles. So what that looks like from our perspective on Earth is that the dark matter is moving towards us. So this is essentially our beam of particles. So in the same way that Dune will send neutrinos from Fermilab to surf and study the nature of neutrinos, we can study the nature of dark matter because the universe provides us with this particle beam of dark matter. Okay, so let's imagine, building a detector target on Earth, and as Earth is moving through the galaxy, we're going towards these dark matter particles. What we're hoping to see is a dark matter particle interacting with our detector target. So this type of scattering, and what will happen when this occurs, what we hope will happen, is that the dark matter particle will give some energy to the target material. So the atom in the target will be bumped, and we'll get some energy. Okay. The catch here is that this is an extremely rare process. Okay, so our latest limits on how strongly the dark matter interacts tells us that we'll see less than one event in a ton of target material in a year. Okay, so this is an extremely rare process. And so that's a real challenge. How do you detect something that's extremely rare? So you have to build a very sensitive detector, but at the same time, avoid all the backgrounds from other particles that we already know about and don't really want to study. So the obvious thing we do is we go a mile underground. So that's the thing that sort of unites all of the research at SURF, is we like to go underground for one reason or another. And for LZ, we're going underground to get away from cosmic rays, which would be swamping our detector if it were on the surface of the Earth. So we're in the Davis campus, which of course is famous for this experiment led by Ray Davis studying solar neutrinos, and Ray Davis actually won the Nobel Prize in Physics for this research. So big shoes to fill, and a big thing to follow. The other thing we do is we have to screen all of the materials that go into building our detector, because everything is radioactive to some degree. So this is actually a picture from the Black Hills Underground Campus, which is at SURF. We have these really high sensitive detectors which can measure the trace amounts of radiation in different materials. And a lot of the materials that we use to build LZ were screened at SURF as well. The other thing we have to do is build our detectors in clean rooms. Dirt and dust, which can attach to the detector, is itself radioactive. So we need to limit how much dust we get on our experiment, so we're in a clean room. We're also in a radon-reduced clean room. So radon is a noble gas that's present in air, and if it gets into our detector, as we run our experiment, the radon can outgas, and essentially our experiment will just be seeing radon rather than the dark matter signal that we're looking for. So these are all things that we have to do to try to mitigate the backgrounds for our detector. It's a really important part of doing this experiment. Okay, so coming back to this picture, I didn't really specify what type of target we're using. For LZ, we're actually using xenon. I'm going to explain why here in a second, but let me just segue slightly and show you. This is basically in a way of showing the history of direct detection of dark matter and how different experiments have performed over time. So this is kind of like a scorecard, essentially, of the different experiments that have been done. So on the y-axis here, I'm showing the cross-section for WIMPs to interact with our type of matter. Okay, so this is essentially telling you the strength of that interaction. And on the x-axis is the WIMP mass. We actually don't know the mass of the dark matter, so we have to compute the cross-section for each of these WIMP masses. And a line on this graph here basically indicates that everything above it has been ruled out. So an experiment took place, and if dark matter had a cross-section at a given mass that's anywhere above these lines, those experiments would have seen a signal in their experiment. So lower on this plot means that you've done better, you've had more sensitivity. And what you see is that most of the best limits here are actually from xenon-based experiments. So Panda X, which is in China, Xenon, which is in Europe, and even LUX, which is the predecessor to LZ at SURF, have set the best limits. This plot was made before LZ turned on, and so that's why the LZ lines are not shown here. And we'll see later in the presentation where they lie with respect to the other experiments. Okay, so why is xenon so good? Why is it performing the best? Well, one of the big reasons is it's a very high density material when it's a liquid. It's 3 times heavier than water. And so that means that you can have a target which has a very large mass for a given volume. It also self-shields, which means that the outer layers of xenon block background radiation from the outside in the outer layers, and that leaves us with this inner target, which is really quiet, and that's really important for having dark matter sensitivity. Some other things we like, it's actually really easy to clean for most impurities. So we can circulate our xenon through a purifier and do some online purification as we run our experiment. There are no problematic long-lived isotopes, so there are no isotopes of xenon, natural xenon, that are radioactive. And that's really convenient. We don't have to worry about somehow purifying or enriching our target. It's also got a really large atomic weight. So it's a very heavy nucleus. And that means that as the dark matter particles come in, they coherently scatter with the entire nucleus. Okay, so the rate of interactions is boosted because of that fact. So this is kind of illustrated on the plot below. So what I'm showing here is the rate of dark matter interactions in some units for a particular cross-section and a given WIMP mass. And it's a function of the energy threshold of the experiment. So essentially, imagine you're integrating an energy spectrum up to a certain point. You can see that if you have an energy threshold of less than 10 keV, which is perfectly achievable in these experiments, then xenon gives you the biggest rate. So this is one of the main reasons why xenon is performing so well. All right, so the final kind of piece of this is, well, this interaction happens, what do you actually see? What do you actually detect? So when the dark matter particle bumps into an atom in our experiment, it can produce 3 detectable signals, some heat, some light, and some charge. And in LZ, we're looking for 2 of those signals, which is light and charge. So how does our experiment actually work? How do we detect those signals? So we're using what's called a two-phase time projection chamber, or a TPC. So when there's a particle interaction inside of our detector, it produces two detectable signals. The first is a prompt scintillation light, and we call that the S1 signal because it's the first. At the interaction site, you also get some charge produced, so some electrons, and we drift those electrons under an electric field, and they're drifted to the top of the detector where there's a gas-liquid interface, so that's why it's a two-phase TPC. And at that gas-liquid interface, the electrons are extracted from the liquid into the gas region, and it produces a secondary proportional scintillation light. And we call that the S2 signal because it's the second one we see. And we detect those light signals using photomultiplier tubes, which are light sensors arranged in arrays at the top and the bottom of the detector. So this is what a real event waveform looks like in LZ. So this is an actual event from our detector. So you can see in this image, you see first the S1 pulse. This is the green pulse that I zoomed in on. And you can see its width here, 300 nanoseconds. And then sometime later, we see this larger S2 pulse, which is a little bit wider. That's the pulse that's in the blue here. So this is a really nice clean event. And these are the type of events we're looking for, where we have an S1 and an S2. And if we have that S1 and S2, we can determine a few things about the interaction that happened inside of our detector. We actually know the position of the event. So this is kind of like a 3D imaging technology. We know the depth of the event because we know the time separation between the S1 signal and the S2 signal. So we know how long it took for the electrons to drift up to the top of the detector, and that tells us what the depth of the interaction was. And we know that to some sub-millimeter precision. We also know the lateral position of the event because we can see which PMTs saw the light from the S2 signal. So where along the XY plane did this interaction happen? We can determine the energy of the event because we know how much light was produced. And one really great thing we can do is do some kind of particle identification. So we know something about what type of particle produced the interaction inside of our detector. So to explain that, let me just introduce this plot, which is actually how we like to look at our data. What I'm plotting here on the right, on the y-axis, is the amplitude or the magnitude of this charge signal. So that's the S2 signal. And then on the x-axis, I'm plotting the magnitude of the light signal, or the S1 signal. And what's plotted here are two calibration data sets. So the first is from tritium. This is a very low energy beta decay. So it's a radioactive source that we actually injected into our dark matter detector, but it's all to calibrate the experiment. And we can remove the tritium after we've finished with the calibration. Okay. So we inject this tritium, and when it does a beta decay, the particles that it produces, they really want to push on the electrons in the xenon target. Okay, so they do what's called an electron recoil, and they produce this population, which is in the blue. The other data that's plotted here are some neutron calibration. So this is neutrons that we make from a deuterium fusion generator, and we've directed those into the TPC, and those neutrons have pushed on the nucleus of the xenon atom. So they've made a nuclear recoil, and they give us this orange population here. So what you can see is we have a way to differentiate between the nuclear recoils and the electron recoils inside the detector. And this is really important because the signal that we're looking for, the WIMPs, they produce the nuclear recoils, and most of our backgrounds produce electron recoils. So we have a way to differentiate between the backgrounds and the signal that we're looking for. And this is essentially limiting or reducing our backgrounds and making our sensitivity. Okay, so this is what the TPC actually looks like in reality. So on the left-hand side is a picture of the TPC after we completed assembly in a clean room at the Surface Assembly Lab at SURF. On the right-hand side, you see a picture of us mating together the top half of the detector, which is the extraction region where the electrons are extracted, and the drift region, which is the main part of the detector. On the bottom right, you can see this array of photomultiplier tubes, and they're all looking upwards, so they're ready to see the light that's being made inside of the TPC and give us our signals. The LZ experiment as a whole, it's not just the TPC. So the TPC is in the middle. That's where we see the dark matter interactions. But we also have a couple of other detectors here. So just outside of the TPC, but still inside of the cryostat vessel that holds the xenon and keeps it at liquid temperatures, we have what's called a xenon skin region. And then as we work outwards even further, outside of the cryostat, we have some acrylic vessels that we fill with gadolinium-loaded liquid scintillator, and we call that our outer detector. So the reason we have these two extra detectors is it gives us a way to tag and veto background events. And in particular, the outer detector is very important because that can tag neutrons, which, as we saw from the previous slide, the neutrons can also push on the nucleus of the xenon atom and would be indistinguishable from the WIMP signal that we're looking for. So this is a very dangerous background that we have to come up with a way to mitigate. So what the outer detector can do is if a neutron goes in and interacts inside the TPC, it can see that neutron on its way out. So it can capture that neutron and tag that event. So this is a way for us to essentially veto some of the backgrounds. All of this sits inside of a big water tank, and the water tank is essentially there to shield us from the outside. So the Davis cavern, which is a lot of rock, which create gamma rays and neutrons. Those gamma rays and neutrons are blocked by the water tank, so it's shielding the inner detectors and again, improving our sensitivity. Here's a quick timeline of LZ operations to date. So I'm picking things up in 2019, which is when we finished the assembly of the TPC on the surface. We took some time to integrate everything with all the underground detector systems through 2020 and the first half of 2021. We then subsequently filled our outer detector and water tank, and then we filled our xenon detector, and then we began our first science run. So this got underway just before Christmas in 2021. We had a first run, and then we posted some results. And those were subsequently published in physical review letters. After the first run, we did some post-run calibrations and some optimizations of our running. And since early 2023, we've been in this long science campaign. What we decided to do earlier this year was basically cut off our data. So we said, okay, we're going to analyze all of the data up to this point and try and release a new result. And I'm going to show you some details here in a second. The first results were announced in July 2022. This was actually a webinar hosted by Surf. So if you go on YouTube, you can actually find this video and watch all of the details. Let me just give you the headline, which is that we looked for dark matter with 60 days of data, and we didn't find anything. So what we concluded was that the data that we had was consistent with all of the backgrounds that we were observing. And that allows us to place upper limits on how strong the dark matter interacts with the ordinary matter. So this is what this is. The solid line is our LZ limit. At a 90% confidence level, it means at 90% confidence, we've excluded everything above this line. You'll sometimes see experiments have some other lines when they post their results. And the reason we do this is because any one run of the experiment is subject to some statistical fluctuations. So what the dashed line on this plot shows is our median sensitivity. That's basically what would a median experiment of LZ's type, what sensitivity would it have had? And then the yellow and the green bands are the 1 and 2 sigma sensitivity bands. So 68% of LZ-like experiments should live inside of the green band, and 95% should live inside the yellow band. So when you see results like this, that's what those bands mean. We actually have some new results. Let me just give you the result, and then in the later slides, we'll talk through the details. So what we've done is added 220 days of data to the 60 days that we had originally to give us 280 days. And in that data set, we still didn't find any dark matter. So we're able to place some upper limits again. These are much stronger than the results we released in 2022. So you can see those results are in purple on this new plot. And then our new limit, combining all of the data, is the solid line here. So let's go through the details. We can come back to this and talk about what this means. So I thought I'd begin by just, basically outlining in general terms, what's the strategy that we use to look for dark matter. So the first thing is we need some really good models of what the signal will look like in our detector and what the backgrounds look like. And we do this through a variety of means. We have computer simulations of how we think our detector is responding to particle interactions. And we tune those computer simulations on calibration data that we take with our detector. So we have a model that we know is really well verified because it can reproduce the calibrations that we do with our detector. We can also use some of the data itself. So not the type of data that we're using for the dark matter analysis, but we can look in what we call sidebands and use that data to understand the magnitude of the backgrounds that we have in situ as the experiment is running. So it's a really good measure of what our backgrounds are, and these are really well constrained. To actually model the signal, well, we combine a bunch of different information, knowledge of the distribution of the dark matter in our universe, how fast it's moving, and how it would interact inside of our detector. The second component is we actually look at our data and we actually refine the data a little bit to select only the events that we're interested in. So a simple example here would be we want to only look for events that had a single interaction inside of the TPC. If we look for those that had multiple interactions inside of the TPC in a given time window, we know that those can't be dark matter because dark matter is so weakly interacting, it would never interact twice in such a short time span. And so that's one way that we can refine the data, is essentially rejecting those events. There are others as well, but what we get in the end is some refined data, and we have our models of our signals and our backgrounds. And what we do is some statistical tests. Okay, so we're asking, does the data look just like the backgrounds, or does it look like the backgrounds plus some signal on top? So I tried to sketch this out here on the top right. So imagine we had a model of our backgrounds, which is in the blue box, and imagine we had a model of our signal, which is the red box. And we had some data points. How do we tell if this data is consistent with seeing just the backgrounds or the backgrounds plus the dark matter signal? And so we do this statistical method called a profile likelihood ratio test to basically see, are we seeing enough events here to be confident that we have a signal? And if we don't have events to see a signal, what is the smallest signal that we might have been able to see with our experiment? And we can set an upper limit in that way. Okay, so background modeling is very important, obviously, as we've just seen. And so let me just give you a quick overview of the background model for our latest data. So these are all of the electron recall backgrounds in our new data set. And the biggest contribution here is from lead-214 beta decays. So lead-214 is a isotope on the radon-222 chain. And I alluded to radon earlier. This is essentially our biggest background. And this is coming from radon, which is in the detector materials. It's going into our liquid xenon target. It's essentially dissolved in the liquid. And it's decaying and producing lead-214, which itself is decaying and it produces these beta particles, which can produce single interactions inside of our TPC. So that's the biggest background we have. The second biggest is betas from other isotopes and also gamma rays that come from the detector materials, trace radioactivity in the detector materials. The third biggest background are actually solar neutrinos. So this is kind of amazing that I'm sure John McCall and Ray Davis would be surprised to see a physics experiment in 2024 where solar neutrinos, the signal that they actually looked for, is a third biggest background. And then the rest of the backgrounds are xenon isotopes and various decays that they can make. And there's a really interesting one, which is xenon 124 double electron capture, which with this newest data that we have, we've actually been able to observe how this has a slightly different response than the electron recall backgrounds. And we can talk about that in the Q&A if there's some interest. One of the other new things that we did with this latest analysis was we came up with a way to tag this lead-214 background. So this was our biggest background contribution, and this is us trying to do something to limit that background. So the thing to understand about LZ, and it's sort of depicted here in the top right, is that we have two mixing modes that we can use. So two ways that xenon can flow through our detector. One is a high mixing mode where we essentially create a lot of convection inside of the xenon target, and that produces a lot of mixing. And we really like this mode for calibrating our detector. It means when we put some radioactive sources into the xenon, they mix uniformly in the detector, and it gives us a really good calibration. There's also a mode which is lower mixing, and this is really nice for the science search because the flow is quite predictable and coherent, and it limits the amount of radon that's getting into the detector. So that's on the bottom right of these four plots. You see this blue region in the middle. That's basically telling you that the activity of radon there is lower than in the other pictures. We can also, as well as reducing the amount of radon there, we can essentially tag the lead-214 decay. So the way this works is we look for the two alpha decays, one coming from the radon-222, one coming from the polonium-216. Those happen quite close in time to each other. The half-life of polonium-218 is just 3 minutes. So we can identify these two alpha decays, and in that way we know, or we can predict where and when in the detector the lead-214 is going to decay. Okay, so what we essentially do is siphon off a portion of our data where we think the lead-214 decays are going to be. And just to illustrate the effect of that, the lead-214 rate in the untagged sample, so that's all of the other data, is 1.8 microbecquerels per kilogram. You can compare that to 3.9 for all of the data. So essentially what this tag is helping us do is reduce this lead-214 activity by more than a factor of 2. And we use this tagged data set directly when we do our statistical analysis, and this helps us leverage the knowledge that that particular data should have more of this lead-214 background. Okay, so this is our search space again. So generically, we have this charge signal on the y-axis, we have the light signal on the x-axis, and now I've overlaid all of the models that we're going to use to look for dark matter. So we have our background models, which are the gray band here, that's all of the electron recall backgrounds. The xenon 124 double electron capture decays are called out specifically here because they have a slightly different response in the detector. So those are the green contours. There's a background which is in the yellow here. I didn't talk about this, but these are essentially accidental coincidences of lone isolated S1 pulses and lone isolated S2 pulses that can combine together and look like a real interaction inside of the TPC. And we expect to get 2.4 of those events in this particular exposure. And then we have our signal, which is in the pink here, this pink contour. And this is, just chose a 40 GeV WIMP to be illustrative here. So what we're looking for with our data is, are we going to see events in this pink contour or not? So that's what we're hoping to see. So here's our actual data. And you see something kind of interesting here, which is there does in fact appear to be data points inside of the pink region. So did we actually discover something here? Well, actually, no. It turns out that these red points are actually fake events that we secretly injected into our data. And the reason we do this is to try and mitigate any bias when we're developing our analysis. So if we didn't do this, let's say the data was completely open, there might be some bias from the analyzers to tune the analysis to leave some events in this pink region, or maybe they don't believe that we can find dark matter and they remove those events. So by having these fake events there, it scrambles the final result until the very end, when everything is frozen and complete. And this effectively mitigates any experimental bias. So this is a similar technique to blinding, which is done in some other experiments. Only this way we get to look at all of the data. We call this salt because it's kind of like salting this plot with some extra events. So, okay, here's the data with that salt removed. And this is the actual data set that we then do our statistical analysis on. And what we find is what the data is consistent with is just the backgrounds. Okay, so we attempted to fit different WIMP masses to this data along with all of our backgrounds, and we found that the best fit was 0 for all of the WIMP masses that we tested. So these are some things that we like to show when we give out our results. So the top left is a table of all of our background components. The first number is what our model expected there to be for that particular component. The second number is after we looked at the data and fit the data to those models, what did the fit result give us? And you can see that there's good agreement between these two numbers. That's telling us that the data is consistent with the model that we gave it. On the right-hand side, this is just a different way to look at our data. So what's actually plotted on the x-axis here is the distance of our data points from the median of the electron recoil band. And what this is really demonstrating is that the data, which is the black points, and the model, which is the blue histogram, is consistent with each other. So these p-values are basically saying this data is consistent with the backgrounds. So because there's strong agreement with the background-only model, there's no signal. That allows us to go ahead and set some upper limits, and this is the plot that we started at. So this is our new result. So what does this mean? So we didn't find dark matter, but we have a very strong limit here. And LZ now has 280 days of data and is running really well. So if dark matter lives somewhere below this upper exclusion limit that we've set with this current data, we're in a great position to actually find dark matter if it lives somewhere below this exclusion limit. And that's why we want to keep running. So the next step for LZ is to continue collecting data. And we're actually aiming for 1,000 days of search time. So we're not even a third of the way through yet. So there's still a potential, there's still a chance that we could discover dark matter particles. Even if we don't have something that's significant enough to claim a discovery, a hint of something would be fantastic, because a bunch of us are working towards a new experiment. So this is a consortium of the current generation experiments, Xenon and LZ, and an R&D initiative in Europe called Darwin, called XLZD, which is working together to build a 60 to 80 ton xenon dark matter experiment. So this is something that was recommended by the particle physics P5 panel. This is basically a panel of scientists that get together and say, what do we want to do for the next 10 years in all of particle physics? And one of the key recommendations was we should actually build a direct dark matter experiment and build a bigger one. And so this is our effort basically to work towards that. And it says here in the recommendation, preferably sited in the US. And I think I speak for a lot of people when I say it would be fantastic to have this experiment hosted at SURF, given the success of LZ. All right, so I think I should stop there, but thank you very much for listening. Thank you. I have to say thank you to our sponsors and funding agencies and all of the institutions that participate in this research. And special thanks to everyone at SURF for continuing to support the LZ experiment. Thank you.
Very good. Thank you, David. Let's give David a quick round of applause here. That was a great talk. Any questions? Maybe we'll start in the room first. Any questions for David from the room? I can ask some questions, but let's see if there's any online so far. Nope. All right. All right. Questions from Jarrett. You mentioned the lead-214 and the radon in your detector. Does that, I really like those mixing diagrams that you showed. Does that set the fiducial volume? Do you use that to set the volume that you do the analysis in or not?
We actually don't use that particular metric to set the fiducial volume. So that is actually set by a different type of background that we have coming from the side of the detector or the detector walls. And that's really driven by the fact that our S2 signal, our charge signal, gets lost really close to the wall. And so we don't have a good way to essentially reconstruct positions out there. And so that's what sets the outer edge of the fiducial volume, which is this inner portion of the detector that we look for the dark matter. So the mixing and the controlling of the mixing, that really happens in a volume that's a bit smaller than the fiducial volume. But the great thing we've been able to do is we know how to control that. And so that's why we're able to switch between these two modes. And it really enables us to do this tagging because the flow is very predictable in that region. So we actually know where the lead-214 decays are going to be.
We have one online from Mike Kennedy.
Okay.
Florida State.
Yeah, definitely no question there. Yeah, we would love to host XLZD at SURF. Maybe David, you could comment on the schedule for LZ's run and for the nominal schedule for XLZD. I've given large error bars on planning right now, but just say a few words.
No, absolutely. So the original plan for LZ was to run the experiment until 2026. We got a bit of a late start, challenges during construction, particularly the COVID pandemic, which delayed us a little bit. So we actually asked for an extension through to 2028, and that would enable us to get this 1,000 days of data. So that's sort of the timeline for LZ. We want to run until 2028. XLZD, so some of that work, designing and selecting where we want to host the experiment, those types of things, will happen in parallel to LZ finishing. But really, most of the optimistic scenarios, I think, really predict us coming online early 2030s, probably mid 2030s. So those are the timescales involved. So LZ is really important because, well, we could still find dark matter, but it really allows us to be doing science up until that new experiment is built. And that's really going to sustain this type of research. So that's really why we want to complete the LZ program and get this full 1,000 days of data.
Very good. Not coincidentally, that 2030s timeframe is the timeframe for our expansion on the 4850-foot level. There is another question online from Dale. Very good. Is a lowering of the detection threshold from 60 days to 280 anticipated with the next run?
Yeah, that's a good question. I didn't really talk much about this. So the result that I showed you guys today, it actually uses a threshold that's a bit higher than what we know we can go down to. And the reason we made that choice was because we really want to do a dedicated analysis of boronate neutrinos from the sun. So it would be a fantastic demonstration of our technology if we could detect the very few events that we expect from a known source, which are boronate neutrinos from the sun coherently scattering in the detector. And all of those events would live at a low threshold, so low energies. So what we decided to do for this particular analysis to make sure that we're not mitigate or biasing that analysis of the low threshold events was set a threshold for this analysis, which was a bit higher than what we know we can go down to. Eventually, what we'll do is we'll use that lower threshold data not only to look for boronate neutrinos, but also low mass WIMPs. So as the analysis develops and in future results, we'll be releasing some results that lower the detection threshold and broaden our sensitivity to the low mass dark matter.
Actually, those pesky neutrinos could become a signal for a supernova. Is that true?
That's right. Yeah. So LZ is actually part of this. I think it's called the SNOOZE network, which is like an early warning system for a supernova. So LZ is able to see some supernova neutrinos and is part of this sort of global network of experiments that will be alerted if there's a supernova somewhere close to us, which would be very exciting.
Very good. Any other questions from the room and online? How are we doing for time? Now we're pretty close. Going once, twice, thrice. All right. Well, thank you, David. Let me just wrap up with a couple statements here. Of course, another reminder that this presentation is available on the Institute website, so you can watch it over and over and over and over again as you might want to. Next month's Deeper Talks in November is TBD, but we are planning that on November 13th, back to our regular time slot of 9 a.m. Mountain Time. And stay tuned for the topic for that discussion. The chat on Vimeo should contain a link to the survey. We would love to hear your feedback on today's event. For those in the room, there are QR codes that you can scan as well to participate in that survey. Thank you, everyone, for participating. Thank you, David, once again for joining us and giving such a great talk on LZ. And until next time, thanks.